We have our next talk by Ivan Perez on functional reactive programming. I think Ivan wins the award for most talks in one day. This is his first of 3 today, and plus he had an experience report at ICFP here earlier, so I'm glad we get him when he's nice and fresh, so take it away.
First, let's do this. Can you hear me? Yeah. All right. Can anybody let me know when I have about 10 minutes left? Can someone keep an eye on the? Yeah. I tend to lose track of time.
How much time do you want to rush?
Maybe 5 minutes.
Sure.
Okay. All right. So thanks everybody for making it, for being here and staying till FARM. It's a pleasure to be back at FARM. And today I want to talk about functional reactive animation, the way that it was kind of envisioned originally, and kind of bring everybody back to the original concepts. So probably many of you have heard the concept or the term FRP, Functional Reactive Programming, and that's an idea that was kind of came to be around the 90s, mid-90s. And FRP is an abstraction to describe systems that vary over time. And over the years, the term was kind of diluted and used to describe systems that were not necessarily over continuous time, not necessarily functional. They didn't have the notational semantics, and kind of the term lost its meaning. But FRP, at its core, is a temporal framework. The keyword in FRP is missing. The keyword in FRP is time. FRP is about time, and FRP is about meaning. It's about focusing on what you mean to say, and the meaning of things, and the notation. And over the years, there have been tons of libraries. This is first page, I think, of 3 of FRP libraries on Hackage, the Haskell package database. And it's very easy to create your own. It's very easy to create your own library. I think the core components of an FRP implementation are about, I think it's just 8 primitives and combinators. So it's very tempting to create a new one. And there have been, when I started my PhD, I counted up to 50 implementations that were in the wild. And these implementations get abandoned. People move on, they do other things. So if you start using one of them and learn one of them, chances are your code in a few years is not going to work anymore because nobody's maintaining that library. And they don't necessarily follow, as I said, the principles of FRP as originally imagined. And people get confused. This is a very common question on Stack Overflow. People saying, how do I make sense of this ecosystem, right? So much so that one of the most popular FRP projects is called the FRP Zoo, which just tries to help people make sense of the ecosystem and explain a few examples how you would write them in different implementations, right? And this is kind of like the landscape of all of these reactive flavors. There's a lot of concepts that are related. There's functional reactive programming as explained by Connell Elliott and Paul Hudak. But then people create implementations that are functional and reactive. And they call them functional reactive, but they're not the same functional reactive that Connell and Paul Hudak created. And then there's also reactive programming that touches on these things. And we have stream programming languages, and people create functional reactive libraries on top of stream programming languages, and no one really understands what they are. And then there's monadic stream programming, and you can implement all of those ideas on top. And then there's temporal logics and runtime monitoring. They're kind of all connected. Don't take those boundaries too literally, like I just did it quickly. But the point is that these things overlap, but the boundaries are not clear. So what I want to do today is kind of to bring everybody back to the original concepts and to show how you could manifest basic constructs in FRP, and also how you can do so in a library that is maintained, is actively maintained, and has been maintained for more than 20 years. And will continue, presumably, will continue to be maintained. So the key takeaways of this talk is that when you describe these systems, these time-varying systems, and we're going to use animations, but you could use it for many other things. People have used it for robotics. People have used it for epidemiology, like all kinds of things. You should focus on the meaning. And the second takeaway is that you should focus on simplicity. It's very tempting to start trying to optimize your code too early on. And if you focus on simplicity and compositionality, then you will get a lot more out of your code, and it will be easier to understand, easier to debug, test, and so on. So to get everybody up to speed on how to draw, we're going to use Gloss. It's a Haskell library for pictures. It's very, very simple to use, as just a few primitives and combinators. And the main data type in Gloss is one of a picture. So for example, you can define a black circle, which has type picture, with the primitive circle solid, and then you give the radius, and that's it. There's a function that you have to call to paint any picture, and when you call it, that's what you get. So I think everybody can kind of follow that. You can apply the color orange, the color constructor to a picture. You just have to pass a color in another picture, and then it changes the color of the picture, right? It's kind of pretty easy to use. This is not my work. This is someone else's work, just to clarify. And you can move pictures. You can use the translation to move a picture to the left, and you can put pictures together. So you can take one, move it to the left, take the other, move it to the right, put one on top of the other, put them in an array, and then with the pictures constructor, you can kind of take a list of pictures and create a new picture. So it's, again, this idea of combinators. You can, scale pictures. Here we put 4 together at different zoom levels. The scaling takes the horizontal and vertical scaling, so you can stretch something sideways or up and down. And you see that it's scaling applied to the same picture. So this down here would be a picture. And it's a pure language. One of the important things is there's no I/O going on in these definitions. There's no side effects. So you can use all the power that you have in a language like Haskell to write your expressions. Here we're using list comprehensions to go through a list of points and a list of scaling factors, and then apply a function based on those. So we're using just key functional programming concepts. You can, of course, rotate them. We'll use this a lot in our examples. And you can also draw with lines, which we probably will not use, but just to illustrate how the library works. Okay, so if you were to write an animation using this library, how would you do it, right? At its core, an animation is just a function of time. It's a function that for any time presents a picture, right? You can think of it that way. You can think of it as a function that for any real time puts a picture on the screen. In the same way that, for example, you could think of a melody as something that for any time puts a sound or plays a sound. And sorry, I know that there are experts in music here, and I'm not, and probably that's insulting someone already. But you get the gist of it. It's something that varies over time. So you could use an abstraction like this to create animations and things that vary over time. You presumably, like for example on the left, you have a definition of A, which varies over time, and then you could say that B is defined in terms of A by sampling A at the same time and then subtracting 1. And then what you would get is that the signal on the left and the signal on the right is the same as on the left, but going down by 1 unit, right? So in principle, you could do something like this. And this is what it would look like if you took the pictures that we saw before and you extended it in the same way, just taking time as an argument and using it in your code. So if you were able to draw this, it would be a circle, an orange circle that moves towards the left as time moves forward. because the translation, moves to the right as time moves forward, because it's being translated by the amount of time, right? The problem is that it doesn't quite work well if you do it that way. And the reason is that, imagine, for example, that you want to write a program that is interactive. So in this abstraction, you could say that the mouse position is also a signal of time. It's something that varies over time. So you might want to draw a moving picture that is at the mouse position by saying, well, the picture at a particular time is going to be a circle positioned where the mouse position is at that time. So the mouse position also takes a time argument, and you query it, you get the two coordinates, and then you position the circle. The problem is that you can do this and say, well, give me the mouse position at a time plus 3. And now how do you run it? Right? Because that's the future. Or you could say, give me the mouse position a year ago. And that means you have to keep a year's worth of mouse positions. Or that number could be determined at runtime, so you don't know how much you have to keep. Maybe you didn't even look at that time. You didn't sample. You sampled right before, right after, but not exactly at that time. So how do you interpolate? So all the temporal languages and frameworks create some sort of abstraction over things that vary over time for these reasons, because they break causality, they lead to memory leaks, undefinedness, and so on. And in FRP, the main temporal abstraction is called a signal or a behavior. And conceptually, it's what you saw earlier, is a function of time, but there's additional constraints. And in the framework that we're going to use, instead of writing systems in terms of signals, we're going to use something called signal functions. And the idea behind the signal function is if we get the input signals that we're going to we have available, for example, the mouse position and so on, we can define a picture based on the input signals like the mouse position. And the constraint of these signal functions is that they have to be causal, meaning that in the output signal, the value at a time cannot depend on the input signal at a future time. They have to respect causality. And there's, again, a language of primitives and combinators that you can use to define these. So, and these languages prevent you from introducing memory leaks and so on, right? So the way that we're going to use it in this particular talk is through kind of a data flow chart system where signal functions can be connected to one another. You can pass the same input to two signal functions. You can put them in parallel. You can apply a signal function to one input and not the other, and so on. And I'll show you the syntax that we use. This is not necessarily the only way to do FRP. It's just one way to do FRP. Okay? And this is called arrows. I don't know how many people are familiar with this, but yeah, the abstraction is called arrows. So the way that it looks like in code is like this, right? You have a signal function, and instead of writing them from left to right, you write them from right to left. So this is the input of the signal function. You pass it to the signal function, you pipe it to another, and the output you call middle, for example. So this is just the way that you're calling the output of this transformation. And then you put middle here, and you apply these two in parallel, and you pass it to that one, and the output you call final. So now you're defining a signal function in terms of these blocks, and the input to the big thing is called input, and then at the end, the output that you get from all of this transformation, you apply this function transform, whatever that is, and that becomes the output of the whole thing. So you kind of have these building blocks, and then you kind of connect things across, and then you can apply signal functions, and you can also apply normal functions to these things. Does that make some sense? So now I'm going to show you how we use this to draw pictures. The implementation we are using is Yampa, which has been around for many, many years. I'm the current maintainer, but I'm not the original developer. It sees releases every 2 months, like clockwork, like we don't miss a day. And it works with all versions of the Haskell compiler from 7.6, which was released many years ago, to 9.6, which is the latest release. It has been used in industry, in commercial games, and it has been used in 2D and 3D games. So it's a fairly good implementation, but there's others available, and I'm not saying this is the only way to go by all means. So let's take a picture and try to move it around. Yes, thank you. So in this case, we just want to make a picture animated. We don't really depend on anything. We don't have any mouse position and so on. So what we have a signal function in the system already predefined that will give us the current time, and we can use it to query the time, and then we rotate a fixed circle, which is just a circle moved to the right. It's a solid circle that is red, and it's kind of moved to the right and up, and we rotate that thing. So essentially what we do is we take the circle, we displace it, and then we start rotating the whole image, right? And this is what, hang on, this is what we should see, right? So it's relatively simple to draw these things. There's an example in the gloss library. It's a color wheel. I'm not going to go through all the details, but as you can see, you just take a number of colors, and you apply the same transformation. You put one circle here, one color, another here, and so on. And when you do that, you get this cute little picture, right? This is not mine. This was already included in the library. But then you can apply the same transformation as you saw before and say, I'm going to rotate this thing. And I'm going to rotate it by an angle proportional to the time. And in this case, instead of rotating all the time in the same direction, what I'm going to do is I'm going to apply the sine function. And when I apply the sine function, you know, the sine goes like this. So it's going to go fast in the middle, and then slow down at the top, and then fast down, and then slow down, and so on. So when you do that, if you play it, you get something like this. And it kind of moves and then slows down, moves and then slows down, and so on. And you're focusing on what you're trying to say. If you see the examples that I'm showing, there's no notion of sampling. There's no notion of change. There's no notion of updates. It's just the meaning of what you're trying to say. So, okay. Let me just show you one more example, and then we'll go into simulations. So the idea of this one is kind of similar to what we saw. Essentially, we take a circle, we paint it with a color, and then we move it. But the difference is that now we move it by a factor that depends on the time. So we capture the time, we apply some transformation, and then we move it right and in by that factor. And when we do that, we see this effect. Kind of opens and closes, and opens and closes, and so on. So again, very simple expressions that suddenly become very visual, right? So although this is cute, it would be pretty hard to create something like visually appealing and interesting just with those pictures. So I'm going to show you what else we can do with these frameworks. When I talk about simulation, I talk more about physics. And these frameworks also know how to do integrals and derivatives. And that also, it's just an approximation. It's not numerically accurate, but it's enough for a 3D and a 2D simulation, like a basic one, like a game and so on. And they provide these signal functions. So if you put an input signal, out comes the integral or the derivative of that signal, the approximation of the integral or derivative. So we all know from physics, the position of a falling, something that falls from the sky is the velocity is the integral of the acceleration, the position is the integral of the velocity, and that's the position, right? That's the vertical. So we could take a picture, paint it, and then translate it by that position, where the position is calculated using this signal function. And if we do that, and we see this, and you will notice it kind of goes faster and faster and faster. It's a little bit slow, the animation, but at the beginning it goes very slow, and then it starts speeding up. And if you had a bigger screen, it would speed up a lot more. Thank you. So you can play with these ideas and then take physics equations and just put them on paper. And I'm not going to walk you through these things, but essentially the attraction, the force of attraction between two bodies in the universe is determined by this formula, where it's directly proportional to the masses and inversely proportional to the square of the distances between them. So if you put these things, you kind of derive this equation from the textbooks, and you could just write it directly. So you can say that the magnitude of the force is the constant of gravity multiplied by the inverse of the dot product of the position with respect to the center. And then you calculate the vector, integrate, and you get the position. And when you do something like this, you get that kind of animation where you have this at the center of the screen, and this second body gets attracted to this body, goes fast, and is orbiting the central point. And this comes directly from this code, which is just the physics equation. Again, we're focusing on the meaning. We don't have to optimize to make it executable. And as a last example, and then I'll just show you pictures. Okay. We're going to take that and create kind of like a planetary little simulation, like a toy simulation. So we do the same, but we're going to have 4 planets and the moon, and we want to know their coordinates. So we kind of pack them together in a record. And we use the same formula, except that we're also going to take into account the mass of the sun, or the main body around which the secondary one is orbiting. So we have to put it here so that the forces kind of look right. In the previous one, we kind of assumed everything had mass 1. And when you just write the equations, again, from the textbook, and you calculate the positions of the different astronomic bodies. So you say, well, Mercury starts at this position with this velocity, and it orbits around the sun, so I have to put the mass of the sun in the equations. Same thing for all the other planets. And then the moon, I put the mass of the Earth. Thank you. And when you do that, you just paint the circles in those positions, paint little circles using the library that you saw. You get this, right? Which is a kind of like cute little simulation. And I mean, it's not at scale, and it's not accurate because, the equations don't really work exactly that way in the universe. Like planets attract each other and so on. But it's not just that everything's orbiting around the sun and the planets are ignoring each other. But it kind of looks all right. But the funny thing is, if you replace the drawings and use OpenGL to draw, then this is what you get. And this was literally the same FRP code. All right. So now I'm just going to show you a few more things that you can do. But we're done with the code. Don't worry. If you made it this far, then you've made it already. So these are some of the other examples that you will see in the paper. And the paper is executable, so I'm happy to send it to anybody who wants it. It's literate Haskell. The images in the paper are extracted from the LaTeX itself. Here you can just combine things to turn around. And you can also create, this is simple, cute little Wi-Fi kind of symbol. Again, you will recognize the sine function here, right? This is the same as the previous one, except that things are laid out in a circle, but it's exactly the same thing. And there's also an example of something that looks a little bit like clouds that are moving to the left. And these are just circles becoming bigger and smaller, but it kind of creates that effect. And just a couple more. Some of these, if they're not in the paper, send me an email and I'll send you the animation. I'm happy to share. And I'm going to show you, you can also do fractals, because you can compose things, because the language is inherently compositional. So if you start duplicating things and moving them left and right and start composing them, you get little animations like this. And they can get pretty interesting. So this kind of looks a little bit even random-ish, even though it's not. And this is just a small piece of code, just signal functions composed with each other. A short snippet generates an animation like this. So that's it. That's all the animations I had. There's more in the paper. The paper is filled with examples. And again, if you saw something in the video that is not in the paper, I'm happy to send it to you. My goal is to make it longer and longer and add more examples. Yampa is actively maintained. You're welcome to join the project and collaborate. There is another FRP implementation that is related. It's called Dunai. And you're also welcome to visit. And there are things that I didn't discuss, but if you focus on simplicity and if you focus on purity and if you focus on the notation, you get a lot of things for free. One of them is that you get a lot of help for testing. So you get the ability to test in ways that you cannot do in imperative languages, for example. You can also exploit time transformations, make things go faster, slower, or even go back in time. So just to recap, the FRP is a temporal abstraction. That's what it's about. It's not about change, reactivity, updates, propagation, nodes and networks. That if you focus on meaning, then you obtain reusable and compositional code. And that even though these constructions were quite simple, they end up being sophisticated pictures. And anyone can do this. This is attainable for everybody. So that's it. That's all I came to say. I'm happy to take any questions.
All right, we have a couple minutes for questions.
Hi, Amos Robinson.
Sorry. Thank you.
Amos Robinson from ANU. Can you talk more about the distinction of Dunai?
Yeah. So Dunai puts a monad in the. Actually, I don't want to take too long, but yeah. So. Oh, it's okay. Okay, so the implementation of a signal function is like this. It's completely pure. Given an input and the time since the last sample, it gives you the output and a continuation. So in the future, you use this one to simulate the rest of the signal function. In Dunai, you have a monad. And if the monad is identity, then you get the same. Well, if you put time, actually, this doesn't exist. But if the monad was identity, you would get the same thing, right? But if the monad, for example, is maybe, you get signal functions that terminate. Because the output may be nothing. And the continuation is nothing, so you're done. You can't simulate anymore. If the monad is either, you terminate with a result. You may be left with a result or right and continue. If the monad is list, then you can parallelize. You have multiple outputs and multiple continuations, and you decide how to follow it. You can use a reader to pass data to all the signal functions without having to pipe it manually. You can use state. So it's very, very versatile. And there's an implementation called Bird River that gives you all of Yampa's API on top of Dunai. So it's API compatible. You just go to your Cabal file, comment out Yampa, write Bear River, and it works. And yeah, that's kind of the gist of it. Thanks.
Any other questions here?
Hi, yeah, John, Columbia University. Great talk. I wanted to ask, so, since Yampa is implemented essentially sort of as a library within Haskell, and it's very attractive because you get to, express just what you mean, and you can do that, right? As opposed to having to have the cognitive overhead of thinking about an imperative language. But then you're also getting a lot of users who might be interested in making art or sound to or animation to use Haskell. And I'm wondering, in your experience, especially as a maintainer for Yampa, what are some of the difficulties they encounter when trying to use the framework in your library?
That's a good question. I think, so historically in the Haskell community, there's been a little bit of resistance towards arrows. People didn't seem to get it at first. And I've made a lot of effort into conveying the idea that Yampa is not married to arrows. You can use applicative style and so on. I think that's been one factor. Apart from that, just lack of examples, lack of tutorials, things like that, which you are more than all welcome to contribute to, like create your own, right? I think that's been it, yeah. There's no technological limitation, nothing like that, as far as I could see.
Got it. Thank you.
Mm-hmm.
All right, I think there's no questions on Discord, and I think we're out of time, but let's thank the speaker again.